Hello, my kiddos and kiddas. We're looking at arithmetic sequences and partial sums today. When it comes to an arithmetic sequence, so it's arithmetic, the class is called arithmetic, something you may have heard of. It's what my mom took when she was in high school. So she did a lot of stuff with patterns, which math is kind of all patterns if you really think about it. And so, anyways, an arithmetic sequence has a pattern where we're adding or subtracting by the same number every single time. Here I say addition just because you can be adding by a negative number, and that's technically subtraction as well. So we're adding by the same number every single time to get from one to the next. And because we have that really cool pattern of adding the same number every single time, we get to use this formula. So a sub n, which is talking about whatever term number, so the 11th term, the 12th term, the 478th term is going to be equal to the first term plus our term number minus 1 multiplied by our common difference. So whatever number we're adding every single time, we multiply that by our term number minus 1 and then add that to our first term in order to get whatever term we're trying to find. So the 11th, the 42nd, doesn't really matter. Our first example that I'm going to look at is they want us to find a formula for the nth term. So I'm starting at the second one, not the first. I know I'm throwing you a curveball. Anyway, finding a formula for the nth term of an arithmetic sequence whose common difference is 2. That sounds like a very important thing. I'm going to highlight it. And they also tell me that the first term is 7. And so we're trying to find this formula for the nth term. So the fact that there's not like an actual number there, they just say nth term, we're going to keep the n as n. And so they tell me my first term is 7, so that's my a sub 1. So anywhere I have an a sub 1, I can plug in 7. Anywhere where I have a d, so that's my common difference, I'm going to put in 2. Technically, all of that was blue. I'll fix it. Much better. All right, so this means that I'm plugging everything into the equation that we were given. So our a sub n, again, I'm keeping n because this is the nth term here, is equal to, instead of my first term or my a sub 1, I'm plugging in 7 because that's what they said a sub 1 was, plus my n minus 1. Again, we're keeping the n because it told us nth term, and then multiplied by my common difference, which they told me was 2. From here, I'm just going to do a little bit of simplifying. And I don't have any more like terms, so I'm complete. The next situation we're looking at, they want us to find the 6th term of the arithmetic sequence that begins with 5 and 12. So they've told me my first 2 terms in this case now with 5 and 12, and they're telling me that instead of the nth term, we're finding the 6th term. So my n is going to be 6. My first term is 15. And then they give me the first 2 terms because since I have 2 terms, I can find the difference in between, which it will be d. So in order to get from 15 to 12, they did tell me at the beginning that this was an arithmetic sequence. So because this is an arithmetic sequence, I'm looking at what number I might be adding or subtracting in order to get from 15 to 12. Because I'm getting smaller, I know I'm subtracting, or I can say adding by a negative, and the difference between 15 and 12 is 3. So I'm subtracting 3 every time, or adding by negative 3 every time, which means d is going to be negative 3. And now I can plug all this into our handy dandy formula and simplify until I get a solid number. So when I simplify everything down, I end up with my 6th term being equal to 0. And we're done. Sometimes that happens, and that's totally fine. Next, we're going to take a look at an arithmetic series. And so this is the sum of a finite arithmetic sequence. So I say specifically finite. I'm being very specific about that because if it was infinite, if it went on forever, then it wouldn't technically have a sum. It would be one of those issues of the arguments with the infinity. And again, I'm really bored with those arguments and I don't feel like having them on my own channel. So I'm not going to. So when we talk about sum, we're talking about a series and we're going to be finite, so a specific number of terms. So this is our handy dandy formula for an arithmetic series. We're adding together the first term and the last term of the sequence, and then we are multiplying by half of our number of terms, or our number of terms divided by 2, and that will give us the sum of everything. So for this one, I have my first term, so they are telling me the sum of the integers. Integers is pretty important because this is telling me that I'm only looking at whole numbers. So we're looking at our counting numbers in this case. We're looking at the numbers from 1 to 35. They first off have told me my first term is going to be 1. They've also told me that my last term is going to be 35. So the only thing that I'm missing when it comes to my formula is the number of terms. So if I'm going from 1 to 35, including 1 and 35, we have 35 terms. Now that I have all of these variables defined in some way, shape, or form, I'm going to plug them into this formula. And I tend to just like to plug this all into my calculator at once, and when I do that, I end up with 630. And so if I were to add up all of the whole numbers between 1 and 35, including 1 and 35, I would end up with 630. And the last problem that I'm going to go through with you guys is to find the 120th partial sum of the arithmetic sequence. And they start us off with 6, 12, 18, 24, and 30. Of course, they're not going to tell us all 120 because that sounds freaking ridiculous. And specifically when they say 120th partial sum, they mean that you're looking at the 120 terms. So they've efficiently given us our in this case. And I always have students that are like, Miss, can't we just, if there's only like 3 terms, just write out those 3 terms and add them together? Yes, of course you can. But then you have instances where we have 120 terms and no one wants to add those all together. That's freaking ridiculous. So we won't. That's why we have this formula. Lazy mathematicians were like, I really hate doing this. I really hate adding all these things. There must be a pattern. And then they found it. So we also have our first term, which is 6. I also am going to need the last term. So I have this handy dandy little shopping list. I have my in, that's 120. I have my first term, that's a sub 1, which is 6. A sub in, which is the 120th term, I do not have. They stop at 30, which is not the 120th term, which means I need to figure out what that term is, which means I'm going to be going back in time and doing that a sub in formula that we did towards the beginning. Oh, and I've gotten to the point where I have to multiply by my common difference, and I do not know what it is. So going back here, I have enough terms that I can figure out the difference going from one to the next. So it looks like I am adding 6 every single time, which means that my common difference is going to be 6. So I now know my last term. My 120th term is at 720, so I have everything that I need to plug in to find the sum of the 120 terms. And I end up with a sum of 43,560. That is such a large number. Are we surprised? No, because there were 120 terms in there. So you should end up with a decently large number, especially if they are all positive. So that's all that I have for you guys today. If you found this helpful, please like and subscribe. If you think that this could be helpful for someone else, please feel free to share. Spread the love.